Look up at the night sky, a picture of light and darkness. Each point of light is a star, a distant sun, and those points of light gather into islands of light that we call galaxies. Our telescopes can see hundreds of billions of galaxies, each containing hundreds of billions of stars. That is the universe we know, the universe of matter, of light, of visible existence. But what if I told you that this entire magnificent picture, every star, every planet, every cloud of gas and dust that we can see and measure, is just a tiny fraction of reality? What if our entire visible universe makes up less than 5% of the total mass and energy of the cosmos? This is not a philosophical hypothesis. This is the astonishing conclusion that modern astrophysics has forced us to confront. The other 95% of the universe is an invisible ghost, a mysterious entity that does not shine, does not reflect, does not interact with light. We cannot see it, we cannot touch it, but we know it is there because we can feel its weight. Welcome back to Science for Sleep. If this journey into one of the greatest mysteries of the universe sparks your curiosity, a gentle tap of the like and subscribe buttons will help us continue these investigations together. And I would also love to know, where are you listening from tonight? Please feel free to leave a greeting in the comments so we know how far this story has traveled. Tonight, we will begin a hunt for the greatest ghost in the universe, dark matter, and we will explore one of the most daring and strange ideas ever proposed to explain it. An idea that suggests the answer may not lie within our universe, but in a place right next to us, a place we can never see, a fourth spatial dimension. Let us begin. Our investigation begins not with a new theory, but with a quiet observation, a puzzle found in the elegant, spinning motion of distant galaxies. For much of the 20th century, astronomers believed they had a solid understanding of how galaxies should behave. They were thought to be great cosmic whirlpools of stars, gas, and dust, all held together by their own collective gravity. Like our own solar system, where the inner planets move much faster than the distant ones, it was assumed that the stars near the bright, dense center of a galaxy would orbit much more quickly than the lonely stars on its faint outer edges. It was a simple, logical assumption, based on the well-tested laws of Newton and the visible distribution of light. But in the 1960s and 70s, an astronomer named Vera Rubin decided to test this assumption with a new level of precision. She was a patient and meticulous scientist, spending long, cold nights at the Kitt Peak and Lowell observatories, pointing their powerful telescopes at our cosmic neighbors, particularly the Andromeda galaxy. Her method was elegant. She used a device called a spectrograph to analyze the light coming from different parts of the galaxy. By looking at the light from the stars, she could apply the Doppler effect, the same principle that makes an ambulance siren sound higher, pitched as it comes towards you, and lower as it moves away. If a star was moving towards her, its light would be slightly shifted to the blue end of the spectrum. If it was moving away, its light would be shifted to the red. By measuring these tiny shifts, she could calculate the precise speed at which the stars were orbiting the galactic center. Night after night, she carefully mapped the speeds of stars, starting from the bright, crowded center and moving outwards to the dim, sparsely populated fringes. And as she plotted her data, a profound and deeply unsettling picture began to emerge. The stars near the center behaved as expected, but as she looked further and further out, the stars did not slow down. They continued to orbit at the same, blistering speed, right out to the very edge of the visible disk. This discovery, known as the flat rotation curve, was a direct contradiction of everything that was understood about gravity and matter. The galaxy was spinning too fast. The visible matter, all the bright stars, all the glowing gas clouds, did not provide nearly enough gravitational pull to hold on to these fast-moving outer stars. According to the laws of physics, these stars should have been flung off into the darkness of intergalactic space millions of years ago. The entire galaxy should have torn itself apart. And yet, there it was, spinning in a state of perfect, impossible stability. Rubin's data was undeniable, and she found the same flat rotation curve in every spiral galaxy she studied. The conclusion was inescapable. There had to be more to the galaxy than meets the eye. There had to be a vast, invisible halo of some unknown substance, a new kind of matter, surrounding the entire visible disk. This invisible matter, which emits no light, would provide the extra gravitational glue needed to hold the rapidly spinning galaxy together. This was the first, powerful, and irrefutable piece of observational evidence for what would come to be known as dark matter. It was the fingerprint of a ghost, a silent and massive presence whose weight could be felt, even if it could not be seen. The strange, flat rotation of galaxies was the first powerful clue that led us to dark matter, but its role in the universe is far more profound than simply keeping stars in their orbits. Dark matter is not just a minor, curious addition to the cosmos. It is the dominant ingredient. The latest measurements, from a variety of sources including the cosmic microwave background and observations of galaxy clusters, all converge on a startling recipe for our universe. The ordinary matter, the stuff that makes up every star, planet, tree, and human being, accounts for less than 5% of the total mass energy content of the cosmos. Dark matter, this invisible and mysterious substance, accounts for roughly 27%. The rest, about 68%, is the even more enigmatic dark energy, which drives the universe's accelerated expansion. This means that for every kilogram of matter you can see and touch, there are more than 5 kilograms of invisible matter out there, shaping the universe with its silent, gravitational influence. We are, in a very real sense, the cosmic minority. But dark matter's importance is not just in its quantity, but in its fundamental role as the architect of the cosmos. It is the invisible skeleton upon which the entire visible universe is built. To understand this, we must go back to the early universe, in the hundreds of thousands of years after the Big Bang. The universe was a hot, dense soup of particles and radiation. Ordinary matter, the protons and electrons that would one day form atoms, was constantly being pushed around by the intense pressure of light, the photons. This radiation pressure was so strong that it prevented ordinary matter from clumping together under its own gravity. Any small region that started to become slightly denser would be immediately pushed apart by the pressure of the photons. It was a cosmic stalemate. But dark matter, whatever it may be, does not interact with light. It is immune to this radiation pressure. And so, while ordinary matter was being held in this smooth, uniform state, the dark matter was free to begin the slow, patient work of gravity. It began to clump together, forming vast, invisible clouds, or halos. These dark matter halos were the first large structures to form in the universe, the gravitational seeds from which everything else would grow. They created deep gravity wells in the fabric of space-time. As the universe continued to expand and cool, and the radiation pressure weakened, ordinary matter was finally free to respond to gravity. And it was drawn, inevitably, into the deep gravity wells that the dark matter had already prepared. Great streams of hydrogen and helium gas began to fall into the centers of these vast, invisible dark matter halos. It was here, in the dense, protected heart of these dark matter clouds, that the first stars ignited, and the first galaxies were born. The beautiful, spiral galaxies we see today are like glowing islands of visible matter, nestled within much larger, completely invisible halos of dark matter. And this structure extends to the grandest scales. When we map the distribution of galaxies across billions of light years, we see that they are not scattered randomly. They form a vast, intricate network known as the cosmic web, a structure of long, thin filaments and dense clusters, all surrounding immense, empty voids. This cosmic web is not a map of ordinary matter. It is a map of the underlying dark matter scaffold. The galaxies are like faint lights strung along the invisible threads of this immense, dark structure. Without dark matter, there would be no scaffold, no gravity wells, and likely, no galaxies, no stars, and no us. It is the silent, invisible architect that built the universe we know. We know dark matter is there. Its gravitational fingerprint is written across the cosmos, from the spin of a single galaxy to the grand architecture of the cosmic web. But knowing it exists and knowing what it is are two entirely different things. This is the great challenge that has consumed a generation of physicists. It has driven them to build some of the most extraordinary and sensitive experiments ever conceived, not by looking up at the sky, but by going deep, deep into the quiet heart of the Earth to hunt for a ghost. The leading theoretical candidate for dark matter is a hypothetical particle known as a WIMP, which stands for Weakly Interacting Massive Particle. The name is a perfect description. Massive means these particles, if they exist, have a significant mass, which is why they exert such a powerful gravitational pull on a cosmic scale. Weakly interacting means they barely acknowledge the existence of ordinary matter. They do not interact with light, which is why they are dark. And they do not interact through the strong nuclear force or the electromagnetic force. They are thought to interact only through gravity and the weak nuclear force, the same force that governs certain types of radioactive decay. This makes them incredibly elusive, true ghosts of the particle world. Trillions of these WIMP particles may be streaming through your body, through your room, and through the entire planet every single second, and you would never feel a thing. They pass through solid matter as if it were empty space. So how do you possibly catch one? How do you build a trap for a ghost? The answer is that you must create an environment of almost supernatural quiet, a place shielded from every other possible source of interference, and the quietest places on Earth are deep underground. This is why the great dark matter experiments are located in places like the Sanford Underground Research Facility in a former gold mine in South Dakota, or the Gran Sasso National Laboratory, buried beneath a mountain in Italy. By going more than a kilometer underground, scientists use the rock of the Earth itself as a massive shield. This shield blocks the constant rain of cosmic rays, high-energy particles from space, that bombard the Earth's surface and would create a storm of false signals in any sensitive detector. In the heart of these deep subterranean caverns, shielded from the noise of the cosmos, the trap is set. A typical experiment, like the Lux Zeppelin or Xenon projects, consists of a massive, multi-ton vat filled with an ultra-pure liquid, usually a noble gas like xenon or argon, cooled to extremely low temperatures. This liquid serves as the target. The idea is simple in principle. With billions upon billions of dark matter particles streaming through this dense tank of atoms, there is an infinitesimally small, but non-zero, chance that one single WIMP will make a direct, head-on collision with the nucleus of one single xenon atom. If this collision were to happen, the xenon nucleus would recoil, like a billiard ball struck by an invisible cue ball. This recoil would produce two distinct, simultaneous signals. First, it would create a tiny, brilliant flash of light, a phenomenon known as scintillation. Second, it would knock a few electrons loose from the atom, creating a small cloud of charge that would drift upwards in an electric field. The inside of the tank is lined with hundreds of incredibly sensitive light detectors called photomultiplier tubes. These are the eyes of the experiment, poised in the darkness, waiting patiently for that one, single, telltale flash of light. For years, these experiments have been running in the deep, silent dark. Scientists have listened with a patience that is almost geological, sifting through immense amounts of data, searching for that one specific, dual signal that would be the unmistakable signature of a dark matter particle. And yet, after all these decades of searching, the result has been a profound and beautiful silence. There have been a few tantalizing hints, a few unexplained events, but no definitive reproducible detection has ever been made. The ghost has not yet appeared in the machine. This silence is not a failure. It is a powerful scientific result in its own right. It tells us that dark matter is even more elusive, even more weakly interacting, or perhaps something entirely different from the WIMP we have been searching for. The hunt has pushed our theories to their limits and forced us to ask a new, more radical question. If the ghost is not in our world, if it refuses to be found in even the quietest rooms on Earth, then perhaps we have been looking in the wrong place entirely. Perhaps the answer does not lie in a new kind of particle, but in a new kind of reality. The profound and persistent silence from the deep Earth detectors is not a failure. In the quiet, patient world of science, an absence of evidence can be just as informative as a positive signal. This silence is a clue in itself, a powerful and eloquent piece of data. It has told us that if dark matter is indeed a WIMP, a weakly interacting massive particle, then its interaction with ordinary matter is even weaker, even more ghostly than our leading theories had predicted. It has forced the boundaries of our search deeper into the realm of the almost undetectable. And for some physicists, this persistent silence has become a catalyst for a more profound and radical line of questioning. It has prompted them to step back from the hunt for a specific particle and ask a more fundamental question about the search itself. What if we are looking for the ghost in the wrong room? What if dark matter is not a new kind of particle hiding within our familiar three-dimensional world at all? What if it is something else entirely, something so strange that it exists just beyond the reach of our senses, a whisper from a place we cannot see? This is the point where our investigation takes a sharp turn, away from the established theories of particle physics and into the speculative, beautiful, and mind-bending frontiers of theoretical cosmology. This is where scientists begin to entertain an idea that sounds, at first, like pure science fiction, but is grounded in the deep and complex mathematics of our most advanced theories. The idea is that the answer to the mystery of dark matter may not lie in a new particle, but in a new understanding of reality itself, a reality that may contain more dimensions than the three we know. To even begin to contemplate this, we must first be willing to question our most basic assumption about the world, that the space we see is all the space there is. We are creatures of three spatial dimensions. We can move forward and backward, left and right, up and down. Our brains are wired to perceive and navigate this 3D world. But what if our perception is limited? What if the universe is a far grander and more complex structure than our senses can reveal? What if our entire, vast, three-dimensional cosmos is just a small part of a much larger, higher dimensional reality? This is the radical idea that may hold the key. Perhaps dark matter is not hiding from us in the dark. Perhaps it is simply living next door, in a dimension we cannot touch, see, or enter, its presence felt only by the one force that can cross the boundary between worlds: gravity. To begin to grasp the immense and counterintuitive idea of a higher dimension, we must first perform a thought experiment. We must learn to see the limitations of our own perception by imagining a world even simpler than our own. This thought experiment is not new. It was beautifully laid out in a satirical novella from 1884 called Flatland, a romance of many dimensions, written by Edwin A. D. Abbott. It is a story that, on the surface, is about geometry, but at its heart, it is about the humility required to imagine a reality beyond the one we can see. Let us imagine this world together. Flatland is a universe that exists on a perfectly flat, two-dimensional plane, like an infinite sheet of paper. The inhabitants of this world are geometric shapes, triangles, squares, pentagons, and circles. They can move forward and backward, left and right, but they have absolutely no concept of up or down. The very idea of a third dimension is not just unknown to them. It is physically and conceptually impossible. A flatlander's entire reality is confined to the surface of their plane. They perceive other objects not as full shapes, but as lines of varying length, as they can only see the edges of their fellow inhabitants. Their society is structured, their physics is predictable, and their world is, to them, complete. They believe that their two-dimensional plane is all that is, and all that could ever be. Now, imagine that you, a three-dimensional being, decide to visit their world. You cannot enter their world in the way they understand it. Instead, you must pass through it. Let us say you gently lower a three-dimensional object, a perfect sphere, through the plane of Flatland. What would the inhabitants of Flatland observe? They would not see a sphere. They cannot perceive depth or height. Instead, they would witness a series of seemingly magical events. First, a single point would appear out of absolutely nowhere as the very bottom of the sphere first makes contact with their plane. Then, as the sphere continues to pass through, this point would expand into a small circle. This circle would grow larger and larger, reaching its maximum size as the equator of the sphere passes through their world. Then, just as mysteriously, the circle would begin to shrink, getting smaller and smaller, until finally, it contracts back into a single point and vanishes completely. To the Flatlanders, this would be a miracle, a violation of every law of physics they know. An object appeared from nothing, changed its size without any apparent cause, and then disappeared into nothing. They might try to explain it as a magical, shape-shifting circle. They would have no way of understanding that they were merely observing a series of two-dimensional cross-sections of a higher three-dimensional object. Now, let's make the interaction more complex. Imagine you gently press your hand through their plane. They would first see 5 separate small circles appear simultaneously, the tips of your fingers. These 5 circles would then move in unison, perhaps growing larger and changing shape as your fingers and knuckles pass through. Then, these separate shapes would suddenly merge into one large, complex, and unfamiliar shape as your palm passes through their world. And finally, this large shape would contract and disappear, leaving them in stunned silence. How could they possibly explain such a thing? 5 objects appearing, dancing, and merging into one before vanishing? It would be the stuff of legend, a divine and terrifying visitation. This thought experiment is the key. It is a powerful and humbling analogy for our own situation. We are three-dimensional beings, living in a world we perceive as having 3 spatial dimensions. If a 4th spatial dimension exists, we are, in a very real sense, the inhabitants of Flatland. We are blind to it. An object from a 4th dimension passing through our world would appear to us as a 3-dimensional object that seems to appear from nowhere, perhaps change its size and shape in ways that defy our understanding of physics, and then vanish. We would be the baffled squares, trying to make sense of a sphere we could never truly see in its entirety. This exercise does not prove that a 4th dimension exists, but it opens our minds. It forces us to confront the possibility that our perception of reality is limited by our biology, and that the universe may be a far grander, more complex, and more layered place than our 3-dimensional minds can ever fully comprehend. It asks us to consider that what seems like a violation of physics in our world might just be the normal, predictable physics of another. The thought experiment of Flatland leaves us with a profound sense of humility. It shows us how a perfectly logical and consistent reality can exist, completely unaware of a higher dimension that surrounds it. And it forces us to ask the same question of ourselves. If we are the 3-dimensional equivalent of the Flatlanders, then what is this 4th spatial dimension that we cannot see? Let us try to build it, not with our senses, which are limited, but with our imagination, which is not. The process is a simple, patient game of extrapolation. We begin with a single point, a dimensionless dot. This is a world of 0 dimensions. It has no length, no width, no height. Now, take that point and stretch it in a single direction. You have created a line. This is a one-dimensional world. A creature living on this line could only move forward or backward. Now, take that entire line and stretch it in a new direction, one that is perfectly perpendicular to the first. You have created a plane, a flat surface like a sheet of paper. This is a 2-dimensional world, our Flatland, with length and width. A creature here can move forward, backward, left, and right. Finally, take that entire 2-dimensional plane and lift it, stretching it in a new direction that is perfectly perpendicular to the first 2. You have created a space, a cube, our familiar 3-dimensional world, with length, width, and height. We can move forward, backward, left, right, up, and down. This is the world our brains evolved to perceive, the world we intuitively understand as the totality of space. But what if the pattern does not stop there? To imagine a 4th spatial dimension, we must perform the same logical step one more time. We must take our entire 3-dimensional space and stretch it in a new direction, one that is perfectly perpendicular to length, width, and height, all at the same time. And this is where our intuition fails us. Our brains, hardwired for a 3D reality, simply cannot visualize this. There is no empty space in our perception for a new, perpendicular direction to exist. Trying to picture it is like trying to imagine a new color that is not a mixture of any other colors. But just because we cannot visualize it does not mean it cannot exist mathematically. In the language of mathematics, it is simple. We describe our world with 3 coordinates, x, y, and z. A 4th spatial dimension would simply be a new coordinate, W. It is crucial here to distinguish this from the concept of time as the fourth dimension. In Einstein's relativity, space-time is a four-dimensional fabric, but it consists of 3 dimensions of space and 1 of time. What we are exploring now is the possibility of a fourth spatial dimension, a fourth direction of movement. To get a hint of what such a dimension might look like, we can again use an analogy. A 2-dimensional being, a flatlander, can see the shadow of a 3-dimensional object. If you hold a wireframe cube above their plane and shine a light on it, they would see a strange, 2-dimensional shadow of a square within a square, with the corners connected. They could never see the true cube, but they could study its 2D projection. In the same way, we can mathematically project a 4-dimensional object into our 3-dimensional space. The 4D equivalent of a cube is called a tesseract, or a hypercube. When we project its shadow into our world, we see a familiar image, a small cube floating inside a larger cube, with all the corners connected. We are not seeing the tesseract itself, only its 3D shadow. If such a fourth spatial dimension were real and large, it would mean that our entire universe, everything we have ever known, might be just a thin, 3-dimensional slice or membrane within a much larger 4-dimensional reality, which physicists call the bulk. We would be living our lives on this membrane, unable to perceive the greater space in which it floats, just as a character drawn on a page is unaware of the room in which the book lies. This is no longer just a thought experiment. It is the foundation of a radical new theory that might just solve the mystery of dark matter. The idea of a fourth spatial dimension, a reality beyond our own, may seem like a purely philosophical or mathematical game. It is a fascinating concept, a delightful exercise for the imagination, but does it have any real basis in the science that describes our universe? The answer, surprisingly, is yes. The whisper of extra dimensions does not come from science fiction, but from the deepest and most ambitious corner of modern theoretical physics, from the decades-long quest to find a single, elegant theory that can unite all the forces of nature. This quest is for a theory of everything, and its leading candidate is a beautiful, complex, and deeply strange idea known as string theory. For most of the last century, physics has been dominated by 2 incredibly successful, yet fundamentally incompatible pillars. The first is Einstein's general relativity, the theory of the very large. It describes gravity as the curvature of space-time and governs the dance of planets, stars, and galaxies with breathtaking precision. The second is the standard model of particle physics, the theory of the very small. It describes the quantum world of particles and the 3 other fundamental forces, the strong nuclear force, the weak nuclear force, and electromagnetism. Both theories are masterpieces in their own right, verified by countless experiments, but they do not speak the same language. When you try to apply the equations of general relativity to the quantum realm, or vice versa, the mathematics breaks down into infinities and paradoxes. String theory is the most promising attempt to build a bridge between these 2 worlds. It proposes a radical and elegant solution. At its most fundamental level, the universe is not made of point-like particles. Instead, the basic constituents of reality are unimaginably small, one-dimensional loops of vibrating energy, called strings. According to this theory, every particle we see an electron, a photon, a quark is not a different type of dot, but is the same type of string, just vibrating at a different frequency, a different resonant note. Think of the string on a violin or a guitar. By plucking it in different ways, you can produce a whole range of different musical notes. In the same way, a single fundamental string, by vibrating in different patterns, can manifest as all the different particles of the universe. An electron is a string vibrating in one way. A photon is the same string vibrating in another. The universe, in this view, is a grand cosmic symphony, and the laws of physics are the rules of harmony that govern how these strings can vibrate and interact. This is a beautiful and unifying idea. But for this symphony to work, for the mathematics of string theory to be consistent and to produce the rich variety of particles and forces we see in our universe, it requires something extraordinary. It requires more space to play in. The equations do not work in our familiar 3 spatial dimensions. They demand that the universe must have many more. Depending on the specific version of the theory, it could be 9, 10, or even 25 spatial dimensions. Why? An analogy might help. A one-dimensional guitar string can only vibrate back and forth, producing a simple set of notes. But a two-dimensional surface, like the head of a drum, can vibrate in much more complex and intricate patterns, creating a richer range of sounds. In the same way, for the fundamental strings of string theory to have enough room to vibrate in all the different ways needed to create every known particle, from the electron to the Higgs boson, they need more dimensions to vibrate in. This, of course, leads to the immediate and obvious question. If these extra dimensions are real, where are they? Why can we not see them? The theory provides a fascinating answer. These extra dimensions may be compactified or curled up at an incredibly small scale, the so-called Planck length, which is trillions of times smaller than an atom. Imagine a long, thin garden hose. From a great distance, it looks like a simple one-dimensional line. But as you get closer, you realize it has a second, circular dimension wrapped around its length. The extra dimensions of string theory could be like that. Tiny, curled-up geometric shapes attached to every single point in our familiar 3D space, too small for us to ever perceive directly. They are a hidden, microscopic texture on the fabric of reality. And so, string theory, our leading candidate for a final theory of physics, does not just allow for the possibility of extra dimensions, it requires them. It whispers to us that the world we see is just a small, unfolded part of a much larger, more complex, and higher dimensional reality. String theory gives us a universe filled with hidden, extra dimensions, curled up into shapes too small for us to ever see. But another, even more dramatic possibility has emerged from these complex theories. What if the extra dimensions are not small at all? What if they are vast, perhaps even infinite, and our entire universe is just a small, three-dimensional island floating within this much larger, higher-dimensional space? This is the core idea behind a set of theories known collectively as the brain-world hypothesis. The word brain is short for membrane, and it is a concept that asks us to completely reimagine our place in the cosmos. In this model, our familiar universe, with its 3 dimensions of space, is a 3-dimensional brain, a vast but thin surface existing within a higher dimensional reality, which physicists call the bulk. Let us return to our analogy of flatland. The 2-dimensional world of the flatlanders is their entire universe, their brain. The higher, 3-dimensional space that surrounds their world is the bulk. They live their lives on a single sheet of paper, completely unaware of the infinite room that exists above and below them. The brain-world hypothesis suggests that we are in exactly the same situation. Our entire cosmos, every star, every galaxy, every point in space we can see or measure, is confined to a single, 3-dimensional membrane floating in a 4-dimensional bulk. This immediately raises a question. If this higher dimensional space exists all around us, why can we not see it or enter it? The theory provides a fascinating answer based on the nature of the fundamental forces and particles themselves. It suggests that the particles and forces that make up our world, the electrons, the quarks, the photons of light, the strong and weak nuclear forces are, in a sense, stuck to our brain. In the language of string theory, these particles are the vibrations of open strings, and the endpoints of these open strings are permanently anchored to our 3D brain. They can move freely along our 3 dimensions, but they cannot leave the brain and venture out into the bulk. It is like a drawing on a piece of paper. The ink particles are part of the paper. They can form intricate shapes anywhere on the page, but they cannot lift off the page and float into the room. In the same way, the light from a distant star can travel for billions of years across our universe to reach our eyes, but that light is forever confined to travel along the surface of our brain. We cannot see into the higher dimension because the very light needed for seeing is unable to leave our world. This is a beautiful and elegant way to explain the hidden nature of extra dimensions. They are not small and curled up. They are large and right next to us. But we are effectively blind to them, because the fundamental forces of our existence, are trapped with us on this cosmic membrane. Our universe, in this view, is a self-contained ecosystem, a ship sailing on a vast, invisible ocean, whose passengers can never leave the deck. But if this is true, if we are so completely isolated on our brain, how could we ever know that the higher dimensional bulk even exists? The answer, as we will see, lies in the one force that may not be stuck to our brain at all, the one force that can travel between worlds: gravity. The brain-world hypothesis leaves us with a profound and humbling image of our reality. Our entire, vast universe may be nothing more than a thin membrane, a single three-dimensional surface floating in a higher dimensional space called the bulk. All the matter and energy we know, every star and every galaxy, is confined to this cosmic sheet, unable to perceive the greater reality that lies beyond it. But the theory does not necessarily stop with just one brain. If the higher dimensional bulk exists, what is to stop it from containing more than one? This is where the idea leads to its most staggering and beautiful conclusion: the possibility of parallel universes. The theory allows for the existence of other brains, other three-dimensional universes, floating parallel to our own within the same four-dimensional bulk. Imagine a stack of paper. Each individual sheet is a complete two-dimensional world, and the characters drawn on one page are completely unaware of the characters drawn on the page directly above or below it. They exist in parallel, separated by a tiny distance in the third dimension that they cannot access. The brain-world hypothesis suggests that reality might be structured in the same way. There could be another universe, another brain, hovering just a millimeter away from ours in the direction of the fourth spatial dimension, and we would be utterly oblivious to its existence. This is a different kind of multiverse from the branching realities of quantum mechanics. These are not alternate versions of our own world. These are separate, distinct universes, each with its own matter, its own stars, and potentially its own unique laws of physics. The way the fundamental strings vibrate on another brain could be different, leading to particles with different masses or forces with different strengths. There could be a universe next door where gravity is much stronger, or where the speed of light is different. There could be silent universes with no life at all, or universes teeming with forms of existence so alien we could not even comprehend them. And yet, they could be closer to you right now than the screen you are looking at, separated only by a direction you cannot point to, a distance you cannot cross. The inhabitants of this parallel world would live out their entire lives, build their own civilizations, and ponder their own cosmic mysteries, completely unaware of us, just as we are of them. Their light is trapped on their brain, and our light is trapped on ours. We are like two ships passing in the night, silent and invisible to one another, separated by an impenetrable dimensional fog. This idea transforms the empty space around us. It is no longer empty, it is potentially filled with an infinite richness, a layered reality of worlds stacked upon worlds. It suggests that the universe is not a lonely place, but a crowded one, and that we are simply living in one apartment in a colossal, higher dimensional building, unable to hear the neighbors through the walls. The idea of parallel universes, of other three-dimensional worlds floating silently alongside our own, is one of the most profound and mind-altering concepts in modern physics. But it also presents a seemingly insurmountable problem. If these other brains are completely separate, if their light is forever trapped within their own dimensions, and our light is trapped within ours, how could we ever hope to prove their existence? If we can never see, touch, or interact with these other worlds, doesn't that make them a matter of pure philosophical speculation, forever beyond the reach of scientific inquiry? The answer may lie in a fundamental exception, a single force that may not be bound by the same rules as all the others. To understand this, we must first look at the forces that govern our own universe. The standard model of particle physics describes three fundamental forces with incredible precision: the electromagnetic force, which governs light, electricity, and magnetism; the strong nuclear force, which binds atomic nuclei together; and the weak nuclear force, which governs radioactive decay. In the language of string theory and the brain-world hypothesis, The particles that carry these forces, the photons, the gluons, the W and Z bosons, are all vibrations of open strings. The crucial part of this idea is that the endpoints of these open strings are permanently anchored to our three-dimensional brain. They can slide around freely on our cosmic membrane, but they can never leave it. This is why our universe is self-contained. Our light cannot escape to illuminate another brain, and their light cannot cross the void to reach us. But there is a fourth force, one that the standard model does not describe. This is gravity, and in the grand architecture of physics, gravity is different. According to Einstein's general relativity, gravity is not a force that is exchanged between particles in the same way as the others. Gravity is the curvature of spacetime itself. It is the very fabric of the arena in which all events take place. And if gravity is the geometry of spacetime, then it is not necessarily confined to our brain. The theory suggests that while the open strings of matter and light are stuck to our brain, there is another kind of string, a closed string, which forms a continuous loop. These closed strings are not anchored to anything, and the particle that corresponds to the vibration of a closed string is the hypothetical graviton, the quantum particle of gravity. Because these closed-loop strings have no endpoints to tie them down, they are free to travel not just along our brain, but through the higher dimensional bulk as well. Gravity, in this view, is the one force that can leak between worlds. Let us use a simple analogy. Imagine two parallel sheets of paper, held very close together. You can draw on the top sheet with ink, and the drawing will be confined to that page. The ink cannot magically jump to the bottom sheet. But if you take a heavy object and press down on the top sheet, it will create a dent. And because the sheets are close, that dent will cause the bottom sheet to also sag in the same spot. The influence has been transmitted through the space between them, even though the object never touched the bottom sheet. In this analogy, the ink is like light and matter, confined to its own page. The heavy object is a massive star or galaxy on a parallel brane, and the sagging of the paper is gravity. The mass of that invisible parallel galaxy creates a curvature, a dent, in the higher dimensional bulk spacetime. And that curvature is felt by everything within the bulk, including our own brain. We would perceive this as a gravitational pull coming from a source we cannot see. Gravity, therefore, becomes the one messenger, the one ambassador, that can travel between these silent, parallel realities. We cannot see our invisible neighbors, but if this theory is correct, we can feel their weight, and this provides a stunning and elegant solution to the mystery that started our entire investigation. And so, all the pieces of our cosmic puzzle are now on the table. We began with a simple, observable mystery, the strange and impossible dance of the galaxies. We saw how Vera Rubin's meticulous observations revealed that galaxies are spinning far too fast, held together by a gravitational force far greater than all their visible stars and gas could possibly account for. This led us to the concept of dark matter, a vast, invisible halo of mass, a ghost whose weight we can feel but whose form we cannot see. We then journeyed into the strange and beautiful world of theoretical physics, exploring the possibility of hidden dimensions and parallel universes, or brains, floating silently alongside our own. And we discovered a crucial clue, the idea that gravity, unlike all other forces, may not be confined to our universe, that it may be a messenger that can travel between these worlds. It is now time to connect these two extraordinary ideas. It is time to assemble the puzzle pieces and reveal the radical, elegant, and breathtaking solution that the brain-world hypothesis offers to the mystery of dark matter. The theory proposes this: the ghost we have been hunting may not be a new kind of particle at all. The missing mass may not be missing from our universe, because it was never in our universe to begin with. The hypothesis is that dark matter is simply the gravitational influence of ordinary matter stars, gas, planets, and entire galaxies existing on a parallel brane, a universe hovering right next to ours in the fourth dimension. Let that idea settle gently. The invisible halo of dark matter that surrounds our own Milky Way could be nothing more than the gravitational shadow of another, parallel Milky Way. We cannot see this other galaxy. Its light, its energy, every photon it emits, is forever trapped on its own three-dimensional membrane. But its mass, just like the mass in our own galaxy, creates a deep curvature in the higher dimensional fabric of spacetime. And that curvature, that gravitational influence, leaks across the dimensional divide and affects our world. When Vera Rubin measured the speed of the stars at the edge of a galaxy, she was not measuring the pull of some exotic, invisible particle. She was measuring the combined gravitational pull of her own visible galaxy and its invisible, parallel twin. The dance of our galaxy is not a solo performance. It is a duet, a waltz with a partner we can never see, their movements forever linked by the shared music of gravity. This theory is stunning in its elegance because it solves two of the biggest mysteries about dark matter at once. First, it explains why dark matter is dark. It is dark because it is not in our universe. It is made of the same ordinary, light-emitting matter as our own world, but its light can never reach us. Second, it explains why dark matter seems to perfectly mirror the distribution of visible matter, forming these vast halos that perfectly envelop galaxies. It is because the dark matter is a galaxy. The reason the gravitational shadow is shaped like a halo around our galaxy is because the source of that shadow is another galaxy, existing in the same location, just shifted ever so slightly in a direction we cannot perceive. In this view, the universe is not 95% unknown, exotic substances. It is simply much, much larger and more layered than we ever imagined. The great cosmic hunt for a new particle in the deep, quiet rooms of Earth might be looking in the wrong place because the ghost was never in the house. It was just a neighbor, standing on the other side of a dimensional wall, their shadow falling silently across our floor. The theory is breathtaking in its scope and elegance. It proposes that the great mystery of dark matter is not a mystery of a new particle, but of a new geometry, a new dimension hidden from our senses. It suggests that the gravitational pull we feel from the cosmos is the faint, ghostly touch of a parallel universe. But science, in the end, cannot be built on elegance alone. A theory, no matter how beautiful, must eventually face the hard, cold light of experimental evidence. How could we possibly test such an idea? How can we search for a dimension we cannot see and a universe we cannot touch? The search is one of the most challenging and ambitious undertakings in all of science, and it is happening right now in our most powerful particle accelerators and our most sensitive gravitational wave observatories. Our first line of inquiry takes us to the Large Hadron Collider, or LHC, at CERN in Switzerland. This is a 27-kilometer ring of superconducting magnets and particle detectors, a machine designed to recreate the high-energy conditions of the universe just moments after the Big Bang. Here, scientists accelerate protons to near the speed of light and smash them together, creating a shower of exotic, short-lived particles. The fundamental principle behind these experiments is one of conservation. The total amount of energy and momentum before the collision must be exactly equal to the total amount of energy and momentum of all the particles created after the collision. Scientists have incredibly precise detectors that act as cosmic accountants, meticulously tracking every particle that flies out from the collision point, measuring its energy, and ensuring that everything adds up. And it is here that a faint clue to extra dimensions might be found. The theory of brane worlds predicts the existence of the graviton, the hypothetical quantum particle of gravity. As we have discussed, unlike other particles, the graviton is not anchored to our brain. It is a closed loop of string, free to travel through the higher dimensional bulk. The hypothesis, then, is this. In the immense energy of a proton collision at the LHC, it is possible that we could create a graviton, but this graviton would not stay in our universe. The moment it is created, it could escape, flying off into the fourth dimension, into the bulk. We would not see the graviton itself, but we would see its absence. Our detectors would register a collision where the energy and momentum numbers do not add up. There would be missing energy, energy that has seemingly vanished into thin air. This would be an extraordinary result. It would be a powerful, indirect sign that energy has left our three-dimensional brain and escaped into a higher dimension. The search for this missing energy is one of the key, ongoing experiments at the LHC. So far, no definitive evidence has been found, but every collision is a new opportunity to catch a glimpse of a particle leaving our world. A second, even more subtle way to search for extra dimensions involves looking for tiny, almost imperceptible ripples in spacetime itself. With observatories like LIGO and Virgo, we have entered the age of gravitational wave astronomy. We can now feel the vibrations of the cosmos caused by cataclysmic events like the merger of two black holes. These events send powerful gravitational waves rippling through our brain, which we can detect. But what if a similar event were to happen in a parallel universe, on a brain just next to ours? We would not see any light from it. But the immense gravitational disturbance could, in theory, leak across the bulk. It would create a much fainter, but still potentially detectable, gravitational wave in our own universe. We might one day detect a gravitational wave signal that does not correspond to any visible event in a supernova, any neutron star merger in our own cosmos. It would be a ghost signal, a tremor from an invisible cataclysm, the gravitational echo of a collision in another world. These searches are at the absolute frontier of what is technologically possible. The signals, if they exist, are incredibly faint and difficult to distinguish from background noise. But the search is underway. We are no longer just looking at the sky, we are listening to the very fabric of space-time, listening for the faint whispers of a reality that may lie just beyond our own. The theory is now laid before us, a breathtaking and elegant tapestry of ideas. It suggests that the great, invisible ghost we call dark matter might be the gravitational shadow of a parallel universe, a world hovering just beyond our own, in a hidden fourth dimension. If this idea, or something like it, proves to be true, it would represent more than just a solution to a cosmological puzzle. It would be the final and most profound step in a long, humbling journey of human understanding, a journey that has consistently redefined our place in the cosmos. This journey is guided by a powerful philosophical idea known as the Copernican principle, or the principle of mediocrity. It is the simple, yet revolutionary, idea that we do not occupy a special, privileged, or central position in the universe. For most of human history, we believed the opposite. We believed we were the center of everything. The earth was a fixed, immovable stage, and the heavens the sun, the moon, the planets, and the stars revolved around us in a perfect, divine ballet. It was a comforting and intuitive worldview, one that placed humanity at the very heart of creation. Then, in the 16th century, Nicolaus Copernicus proposed that the Earth was not the center. It was just another planet, orbiting the sun. This was a seismic shift in perspective, a great demotion that was met with fierce resistance. But the evidence, from the observations of Galileo to the mathematics of Kepler and Newton, was undeniable. We were not the center of the solar system. We were just one of several worlds, circling a rather ordinary star. For a time, we could still take comfort in the idea that our sun was special, perhaps the center of the galaxy. But in the early 20th century, astronomers like Harlow Shapley mapped the distribution of star clusters in the Milky Way and proved that our sun was not at the center at all. We were located in a quiet, suburban spiral arm, 2/3 of the way out from the galactic core, another demotion. Our star was just one of 100 billion others in a vast, spinning city of light. Then, Edwin Hubble showed that our Milky Way was not the only galaxy. It was just one of hundreds of billions of galaxies, scattered across an expanding universe. The great cosmic city we called home was just a single grain of sand on an infinite beach. With each great scientific revolution, our address in the cosmos has become less and less significant. We have been gently but firmly moved from the center of existence to its quiet, unassuming periphery. And now, the brain-world hypothesis proposes the final, ultimate demotion. It suggests that not even our entire, vast, three-dimensional universe is special. It may just be one membrane, one slice, one bubble in a much larger, higher-dimensional reality. A multiverse teeming with other worlds we can never see. If this is true, it is the ultimate expression of the Copernican principle. It tells us that our universe is not the universe, it is just a universe. This realization does not need to make us feel small or insignificant. On the contrary, it can fill us with a sense of profound wonder. It means that reality is infinitely richer, deeper, and more mysterious than our senses could ever reveal. It suggests that the universe of stars and galaxies we see is just a single page in a library of infinite volumes. And while we may be confined to reading our own page, the knowledge that other books exist changes the meaning of the story entirely. It transforms our understanding of existence from a single, lonely narrative into a vast, interconnected tapestry of possibilities. The mystery of dark matter, in this light, is not a flaw in our understanding. It is a gift, a clue, a gravitational whisper from a neighboring reality, reminding us that we are part of something far, far grander than we ever dared to imagine. And so, our long and quiet investigation comes to a close. We began with a simple, astronomical puzzle, a ghost in the machine of the galaxies. We followed its gravitational fingerprints across the cosmos, from the dance of distant stars to the very structure of the cosmic web. We hunted for it in the deepest, quietest rooms on Earth, only to be met with a profound and telling silence. This silence led us on a new path, a journey not into the heart of a particle, but into the very nature of reality itself. We stepped through the looking glass of a fourth dimension and entertained the most radical of possibilities, that the ghost we have been hunting is not a strange new substance, but the gravitational shadow of a parallel world, an invisible neighbor whose presence we can only feel. This is a theory at the absolute frontier of human thought, a beautiful and untested idea, but whether it is ultimately proven true or not, the journey itself leaves us with a profound and peaceful realization. The mystery of dark matter is not a flaw in the universe. It is a flaw in our map of it. It is a humbling reminder that our senses, the tools with which we perceive reality, are exquisitely limited. They show us a world of light and matter, but this may be just a single, vibrant page in a library of infinite, silent volumes. The Copernican journey, which moved us from the center of creation to a quiet suburb of a single galaxy, does not end there. This final step suggests that even our entire universe may not be the whole story. It may just be one membrane, one slice, one bubble in a much larger, higher dimensional reality. And this realization does not need to make us feel small or insignificant. On the contrary, it can fill us with a sense of profound connection. It means that the universe is not just bigger than we imagine. It is bigger than we can imagine. It is a layered, intricate, and mysterious place, and we are a part of that mystery. And perhaps, in the quiet of the night, as our conscious mind begins to let go, we get a small glimpse of what it is like to touch another reality. The world of dreams is, in a sense, a parallel universe we visit every night. It is a world with its own rules, its own logic, its own strange inhabitants. It is a place we can enter, but cannot fully control. A reality built not from atoms, but from memory and emotion. As you now let your own mind drift into that quiet, internal space, consider this: the universe may be structured in the same way. A world of tangible reality, floating alongside a world of invisible possibility. A universe we can see, and a universe we can only feel through its gentle, gravitational pull. The mystery of dark matter is not a problem to be solved with anxiety. It is a wonder to be contemplated with peace. It is the universe whispering to us that there is always more to the story, always another layer to explore, always a deeper silence to listen to. And in that quiet, endless possibility, there is a profound and gentle peace. Sleep well.